So then the next step was to make a calibration tool for the gyroscope that would let me determine how much to scale the raw gyroscope values by. The website that I was looking at said I should divide by 1024 because that's what felt right. And I said, well, I can probably do better than that. I had been working on the optical tracking for the controller. I said, I know, I'm really smart. I can overcomplicate this. I'll make this tool so that I can sweep the controller such that the tracking bar is in view, and I'll sweep the controller back and forth, tilting the controller around so that I'm getting an optical read for what the orientation of the controller is, in this case measuring the roll of the controller, and then figure out, okay, well, if this is optically what the roll is, and I'm reading at the same time the raw gyro values from the controller, and say, okay, well, how much would I have to scale the raw gyro values to match the optical values I'm seeing? So I did the work, and I tried to make the tool, and I was getting scales of around 850. So that was a little below the 10,024 value that they predicted, but I said, let's try it out. So I tried it, and it was a little bit off. So I was like, okay, let's just try 1024 and see if that works. And it turns out that was pretty close. That felt right. So I probably should have just tried that in the first place to see how that felt, but at least it was an interesting exercise to go through the process of trying to make the tool and see if that agreed with the measurement, if that was a reasonable scale. With the sensor calibration figured out, the next step was to get an optical pose. Now, I already alluded to the optical pose a little bit when I was doing the gyroscope calibration, so this work was going on in parallel, but it makes sense to talk about after the sensor stuff. So the first piece of it is to figure out how we can get an orientation off of that light bar, DS4. So my first thought was like, well, OpenCV, the computer vision library we use for a bunch of other stuff in PSMoveService, has a function that says, given an image, a blob, that a lot of the tracking we do involves extracting these color blobs from the image, compute a best fit triangle around that. And since I have 3 points, I can take those 3 points and compute an orientation from that. So I tried that, and I actually posted a video earlier of that result. One of the problems, though, is that it is a tight bounding triangle, and so if there's any noise at all in the boundary of it, you're going to end up with these very sharp oscillations on the corners, which results in an unstable tracking. So then the next attempt I said was, well, let's try taking the midpoints of those edges and making that the triangle that I use. And so those were much more stable. But then the problem was that when I was trying to solve for the orientation of the controller, there's another method inside OpenCV called solve P&P for the perspective n point problem, where n is the number of points. And the idea is that you have a known set of points, and then you know their 3D positions for, like if the thing's sitting at the origin, what the x, y, z's of those are in real world space, in centimeters or meters or whatever. And then you see those same points as pixels on the screen. So you say, okay, I know this point A corresponds to point A in the real world, and pixel B corresponds to real point B, and so on. And when you have that correlation, you can say, tell me what the transform of that object must be so that I would see it this way on the screen. And you also have to know some properties of the camera, what the focal lengths are and whatnot. And so the problem is that the 3 points wasn't sufficient. It wasn't enough for that solution to work and give you a single answer. So I said, okay, well, then the next thing I can do is construct a best fit bounding box. There's another method in OpenCV for doing that. But then the problem is that you need to know, if you just compute a best fit bounding box, you need to know which way is up. And so the other thing you can do in OpenCV is say, given a blob or an image, compute what's called the moments of that image. That basically tells you where the points are weighted. And so the triangle that we have is top heavy, more points are kind of loaded toward the top. And so that can kind of define an up direction. So once you have the bounding box and the up direction in the triangle, you can end up with this nice set of 7 points, and you can rotate the controller around. And the test video here, you can see I have them color coded. So point 0 is red, the yellow one is 0.1, the green one is 0.2, and the blue one's 0.3 on the square, and then I have similar ones for the triangle. And so as I spin it around, you'll see that they stay as consistent as it doesn't flip, which is a problem earlier. So then with that, we can use solve P&P to get the pose that we're looking for. However, there's one more problem with OpenCV. So it turns out when you're trying to figure out what that best fit transform is, that's actually solving what's called a nonlinear problem. It means that there's some error function that you're trying to minimize the error in. The error in trying to say the transform applied would result in these pixels that got transformed and how much they're off. And there's several local values in that error function. And sometimes if two values are close to each other, you'll inadvertently get stuck in the value you didn't want to end up in. And in this case, that manifests as getting confused between two orientations that are kind of close. And because that sensor bar, especially when you're tilting it up or down, gets kind of narrow, it has a hard time telling whether you're tilted up or down. Technically speaking, if you had perfectly clean measurements, you could distinguish between those two cases because the lengths would be different enough, but in this case it's possible to get stuck. And so what'll happen is you're tilting the controller more than like about 25 or 30 degrees. Sometimes it'll get confused and think you're tilting up when you're tilting down or down when you're tilting up, which is frustrating. So that's where the optical tracking currently sits right now. And the way I get around that for the time being is that I assign this notion of a optical tracking quality based on the number of pixels in screen that I can see of that tracking bar. So the more tilted it is, or the farther away it is, there'll be fewer pixels available on screen, and so I'll trust it less. At the end of the day, all I really need to do is use this to fight drift in the IMU. Because you remember earlier I said that the DS4 has an accelerometer and it has a gyroscope. And those two will give you an orientation, but you'll get yaw drift. So basically, anytime I can see the orientation of the controller cleanly, I can blend that against the current orientation that I had from the sensors. And say, hey, the sensors say that I'm pointing, off at 30 degrees, but optically I can tell you actually should be facing forward, so I can blend into that and correct it. And so what that means, though, is that if I go a long time without seeing that sensor bar, then I could potentially get more drift. And so we need to kind of blend against those two factors. Later on, it also occurred to me that I could take advantage in a multi-camera situation. Rather than trying to use solve PNP, I have these 7 points, this tracking frame around the light bar. And I see those 7 points from the point of view potentially of multiple cameras in a multi-camera system. And so I could triangulate the 3D position the same way that I triangulate positions on the PSMove when you're using multi-camera. And that can give me the real-world 3D locations of those positions. And then I can construct a best fit plan on that and get an orientation that way. That may still have the same problems that the solve PNP does. I don't know, but that's something I'm going to try at some point. So we'll see. That's something I'll have to try to experiment with later. So we spent a lot of time talking about orientation, but the other part of this is the positional tracking of the DS4. Now, fortunately, so long as you see some part of the light bar, it's reasonable to get just pick the center of that and you base the position tracking off of that. And we can do the same kind of triangulation work in a multi-camera situation where if two cameras can see some part of the light bar, we can take the center of that and triangulate those two positions to get a position of the controller. The problem, though, is when you hold the DS4 in your hands, it's actually really easy to kind of tilt it down a little bit out of view of the camera. Now, on the PSMove, in our current implementation, when you lose optical tracking of the PSMove, we just cut out tracking of it altogether. This is not an option on the DS4 because it happens so frequently that it would be incredibly frustrating to use. So we need to leverage the IMU on the DS4 to give us some sense of if we can't see the controller, we need to know if it's moving or not and try our best to interpolate its position based on those sensor values. In this case, the accelerometer is the thing that's going to help us. Now, the problem with the accelerometer is that it's not measuring just one thing. It's measuring the direction of gravity plus any other linear accelerations on the controller. Generally, the force of gravity in that measurement isn't changing that rapidly compared to other movements that you're doing. So there's a couple tricks that people do to try to extract gravity from the accelerometer measurement. One is called a low-pass filter. Low-pass filters are used in audio a lot to cut out signals above a certain frequency. And the implementation of them is usually really simple. It's just this weighted blend, and depending on the blend value you pick between your previous value and the next value, will affect the cutoff frequency, so to speak. And so you can kind of use that same trick to cut out the gravity portion of it. I couldn't get that working very well. So another trick I heard is to actually take the derivative of the accelerometer value, and that gives you this notion of a jerk. A jerk is the name for the derivative of acceleration, and they use it in roller coasters and other things like that, and robotics. And the idea is it's a rate of change of acceleration. And so in this case, the rate of change of the accelerometer should be due to motion of me moving the controller around. So basically take the jerk, smooth it because it's going to be noisy, and then integrate that back upwards. So integrate the jerk to get the linear acceleration of the controller, integrate the linear acceleration to get the velocity of the controller, integrate the velocity to get the position. Now, of course, there's noise and all this stuff, and error that accumulates, and every time you're integrating error, you can very quickly spiral out of control. And in this case, if you have no filtering in there at all, and you don't do anything to suck energy out of the system, so to speak, add a drag force, things blow up really quickly. Like within the order of a couple hundred milliseconds, your controller will go flying off into the horizon. And this is a very known common problem with any kind of IMU-based integration. So in my case, for my initial implementation, I just damped the hell out of everything and added enough drag so that that wouldn't happen. And if you're holding the controller still and you tilt it down, you can't see it anymore, it won't go flying off like crazy. The trade-off with this, though, is that the moment you lose tracking optically, you can continue with the controller around, you can even waggle your hand around crazy, but it will still feel sloppy and weird, and there's still some tuning that needs to be done to make that feel right. And it's never going to feel great. That's a trade-off you make with that. But I'm hoping that the right amount of adjustment to those tuning parameters will make it feel reasonable enough. And depending on the kind of game you're trying to make with this, if you are trying to do some kind of interaction and then go gestural, and in going gestural and reaching out and grabbing something with your controls that you have that occlusion, the gestural motion will be enough. But it's never going to be as good as the PSMove. And part of the thing I want to do to help with this, because right now a lot of these blending weights and things I'm picking are very arbitrary. But there's another kind of filter called a Kalman filter that's used a lot whenever you're trying to incorporate multiple sensors and blend them. And one of the nice natural parameters that you have in there is how much you trust each of your sensor measurements. And it's a value that you can scale up or down and pass in and have it blend over time nicely depending on the tracking qualities of your different sensors, which are changing dynamically in this thing. So the next big chunk of work to make this work better is to implement all this filtering that I've done so far as part of a Kalman filter. We already need to do that work anyway for the PSMove. So I'm hoping that that will help. Because as you can see from the tracking video, it works, but it's not a great experience right now. I can use a lot of improvement. So anyway, this is a lot of talking. I hope that this video was interesting. It's been a really interesting challenge working for this. I'm not a computer vision expert. I'm a game programmer by trade, so I've had to learn a lot of this stuff myself. And I'm sure I've made some mistakes in describing some of these things. So if there's something you hear me say that's wrong, please feel free to call me out. I'd love to hear any suggestions or tips you have. If you think there's something I missed or that is a better way to do it, please feel free to leave a comment. And yeah, thanks so much for watching. I appreciate it.